Step outside and take a deep breath. The air looks clean, but inside that breath are gases you can't see, some harmless, some helpful, and some dangerous. That invisible mix is where environmental chemistry begins. Let's go a little deeper. Environmental chemistry studies how chemical substances move through air, water, and soil, and how they affect living systems. It's not abstract science, it's chemistry happening around you every second. Here's something even more interesting: air pollution isn't just dirty air, it's a chemical imbalance. Gases like carbon monoxide, nitrogen oxides, and sulfur dioxide react in the atmosphere, forming smog and acid rain. These reactions damage lungs, buildings, and ecosystems. But wait, here's the twist. Not all gases are harmful on their own. Greenhouse gases like carbon dioxide and methane trap heat in the atmosphere. This warming effect is natural and necessary, but too much of it disrupts climate balance. Small changes in concentration, massive global effects. Now let's go even deeper. High above the Earth is the ozone layer, a thin shield that absorbs harmful ultraviolet radiation. Ozone protects life, but only when it's in the right place. At ground level, ozone becomes a pollutant. In the upper atmosphere, it becomes a lifesaver. Same molecule, different location, opposite effects. Let's connect this to real life. Air quality alerts, climate change discussions, water treatment plants, environmental laws. All of these are built on understanding chemical reactions in nature. Before we wrap up, zoom out for a moment. Environmental chemistry shows that chemistry doesn't stay in test tubes. It spreads, reacts, accumulates, and affects entire systems. And that leads to the next question. If chemistry shapes the environment, how does water itself get purified, treated, and made safe for daily use? That's exactly where we go next.